slide where you're comparing the various optimizers?
Yes, for any particular, yes.
So for here, for your IPG, are you saying that it has a faster convergence? Like, is the benefit that it converges faster over a shorter amount of iterations, or that it converges better, so you have less of a loss of fidelity?
It's a great question. So we claim both. So when we look at state vectors, so this is the graph of the full unitary, we find that IPG does achieve the lowest cost, but its best run was not the fastest. Okay. When it comes to state vectors, it achieves the lowest cost with the lowest number of iterations, and so that's the difference between those two.
So if you were to, I guess, map your fidelity for an extended period of time, yours would outperform, so you have less of a loss in fidelity than the other optimizers, you would say, in terms of your loss function?
Yep, given the same cost function for all optimizers, consistently IPG has provided the lowest value for cost.
Okay.
And this is important because each epoch has different initializations. So your function is starting at different points on your loss landscape. Mm-hmm. So it shows that it's pretty consistent regardless of where you start your optimization process. Whether you're in a barren plateau to begin with, or somewhere else near another local minima or maximum. Yeah.
Yeah. So looking at this graph, I'm trying to kind of make sense of, I guess, like what I'm seeing here between LBFGS and IPG. So yeah. I see that, as the number of iterations gets like really big, right? The IPG kind of settles down to like a lower, to a lower cost than the than the LBFGS. But like, would I be right in saying that like if we don't care about like the value of the y-axis too much, right? Like, it seems that LBFGS just like it converges to a reasonable value faster. Like in some cases, would LBFGS be more useful, or is it just
you're very right. Yeah, like the difference in cost over here compared to the orders of magnitude we saw for state vectors are a lot different. So in a lot of cases, yes, with IPG achieving a cost only like 2 times smaller than LBFGS, that difference is not as important in this situation. But if you were to approach a brand new problem for the first time, and you weren't sure of your optimizer having consistent convergence, there would be uncertainty as to whether you are achieving the lowest cost it can achieve, unless you ran that same problem over multiple epochs. But yeah, great question. Yes?
So I understand that this whole main idea is that you're trying to optimize cost to get to a specific quantum state. Yep. But why? What is that quantum state overall doing? Like, what's the big idea here?
Yeah, no, that's a great question. The big idea is we have quantum algorithms out there that we want to run because they either in the long term show some quantum advantage, or in the short term show that quantum computers have utility. So, for example, with Shor's algorithm, being able to implement Shor's algorithm means being able to find the factors of very large numbers very quickly. For context, a classical computer, if you tried to get a classical computer to find the factors of very large numbers, it would take almost 2,000 years to do so, which is why we have RSA encryption, which is why we have large strings of bits encrypting our data. But if you were able to implement Shor's algorithm, you would be able to find those factors and break that encryption and unlock all that data. Now that reality is very far away. It requires hundreds of thousands of qubits, as well as better error correcting performance. But a step in that direction means being able to at least get a quantum algorithm that is very close to that algorithm through different optimization methods. I don't know if that answers your question.
How does it like specifically relate to like why are we like trying to optimize a quantum state? I mean, I'm not very well versed in this, so like that made sense, but like why specific quantum states, if anything? I don't know if that's like too intense.
No, it's a good question. The reason we look at specific quantum states is because our quantum algorithms in general rely on the combination of multiple hard quantum states. So we're at the stage where we're trying to first be able to compute these quantum states individually before chaining them together. And so that's what this focuses on. Because our computers are very noisy right now.
So, I'm like sort of along the line of her question. Is it right to say that you're passing these quantum states to and doing operations on them? So this is trying to make sure that you're passing the state that you want to, and not another state that has a bunch of noise. So then your operations send it to where you don't want it.
No, that's good. So for this optimization, we are physically optimizing the circuit classically. We're using, because you can't access state vectors in a quantum sense, because observing a system destroys information. And so we're optimizing an ideal state, an ideal column vector, an ideal matrix to our computed unitary, or our computed state. So yeah, entirely classical in that sense. And then we apply the optimized circuit to a quantum computer to see, hey, does this even work? Yeah. Yes.
I was going to say about the ansatz on the previous slide.
About what, sir?
The ansatz, the like sequential rotations
Yep.
and then snaps over and over again.
Yeah.
So you have that process of rotations and then the C-naughts repeated 5 times over. Is there a particular reason it's 5 instead of more or less, or is that just arbitrary, or is it proportional to the number of qubits, or?
That's a good question. So the depth of the ansatz is just chosen heuristically. It's saying, okay, do we see convergence with, 1 layer of the circuit versus 5 layers of the circuit? So just through experimentation, we found that 5 layers achieves convergence that we are satisfied with.
Okay, so as the algorithm runs, the depth of it actually changes?
No, we physically change the depth, run the algorithm, see if that depth works. If it doesn't, increase the depth.
Oh, okay, so you're saying you ran it with like 1 or 2, and then you ran it with 3, and then you ran it with 4, and then you found that 5 is the best?
Essentially, yeah.
Okay. Is it that 6 is then worse than 5, or it's just not worth the added complexity?
So with most of these ansatz, it's not that if you add more layers, you get better convergence. After a certain time, you end up in a situation where you have too many parameters you're trying to optimize, and you overfit our system. So 6 and onwards, we were overfitting, so less convergence. Yeah.
Could you go to your slide where you have, it's near the end, where you have the comparison between the 2 quantum computers, and you have like bar graphs? Yeah, okay. So could you say a little bit more, what am I looking at on the x-axis?
Yep, so I should label these better. So on the x-axis, you're looking at, so we have a 3-qubit circuit, which means that our output's going to be a probability distribution over 8 states, ranging from 0, 0, 0 to 1, 1, 1.
Okay, that's what you were showing at the beginning. So you've got 3 qubits.
3 qubits and 2 to the 3 states, so you have 8 states. I should label that better.
Okay. And then what can you say the graph after?
The graph here? Or?
Yes, the graph.
So the graph...
Could you explain one more time, why would we expect to see, if you said all 3 qubits, no, I gotta go back to the next one.
Yeah.
So you said all 3 qubits to equal superpositions.
Mm-hmm.
Why would you expect to see 0 state?
I mean, you would expect to see it just by like if you like tensored your states together and like computed it.
It's like the expectation.
Did you run the quantum Fourier transform?
Yes.
On a superposition of all qubits, which
Yeah.
the output of that I think is supposed to be the 0 state. So we ran something on it.
The quantum Fourier transform, in a loose sense, essentially, in a way, computes the periodicity between your different states. So if you have an even superposition, your periodicity is the same between each state, and as a result, you expect a 0, 0, 0 output because you have very even periodicity. If you are running it with a Pauli-Z operations, you have a phase change on your 3rd qubit. Then because of that, it's picking out that periodicity for that 3rd qubit because it's different to the first 2 qubits, and so you have a peak on the 0, 0, 1 state. But that was a good question. Thank you. I think your hand was up, and then we'll go down.
So I just have a question. So what exactly does the cost function here represent? Is it just like the amount of noise in the system, or?
Yep. So the cost function represents. I'll go back to that slide. So in this example, our cost function represents how close our output is to our desired state. So this is the exact unitary we're looking for, and so we subtract this unitary from the unitary coming out of our our circuit each time, and that is our cost function here. When we have column vectors, it's just the inner product.
Yeah.
The inner product tells us how close those two states are. I think, yeah, Nathan, your hand was up.
Yeah, I suppose I have a bit of a technical detail to ask about.
Sure.
You've defined your ansatz here, where you're computing it with the state vector simulator.
Yeah.
In the absence of noise.
Yeah.
And that's definitely classically hard.
Yes.
So I could imagine even for an optimization of 40 qubits, your runtime could get diminished significantly.
Exactly.
Even exponentially.
Mm-hmm.
Is there a plan to handle this? Or
Yep. So there are two ways the industry is handling this, and that we are looking at. One way is looking at non-gradient based methods altogether. There is a paper that came out last year on using imaging to find your minima. The challenge with gradient-based optimization on a QPU itself is that if you're trying to compute your gradients, you are storing hundreds of parameters each single time. That combined with the intrinsic noise of each qubit makes gradient-based optimization challenging on a QPU, which is why we do it on a noiseless simulator.
Yeah.
The other benefit to this is different computers have different gate sets to begin with. And so, for example, with IonQ's gate set, they have their own native gates. So they take the gates you apply, your X, your Ys, your C naughts, and they apply them to their native gate set. And so that optimization itself isn't necessarily quantum in its sense, but they still need to be able to efficiently take your circuit, break it down into their gates, and say, okay, how can we minimize that circuit depth as well? And so that's the other application in that sense. But you are right. If you have some orders of magnitudes of qubits larger than this, then it becomes very challenging to simulate classically, especially if you use non-Clifford gates.
So those are something exponential time?
It'll be I'm not sure the exact time, but
Something exponential?
something exponential, yeah. Yes. Did you?
Is there did you run like the other initial gradient descent algorithms on the quantum computers or no? Like the other methods?
Did we run the other methods on a QPU?
Yeah.
No, we did not. We focused the research specifically on gradient-based methods.
Is there a reason why, let's say for comparison or anything like that, was the simulator sort of like the decision on whether or not you should run it?
Like the decision for using a gradient-based method versus a non-gradient-based method?
Like running it on the quantum computer. Was that like a deciding factor or?
No, the motivation was just that current optimizers we found, even in these 3 to 5 qubit settings, don't achieve very low minima, and it was leveraging the fact that IPG in classical situations is achieving this minima, and because of that promise, saying, can we apply this to a quantum setting? So that was the motivation behind using a gradient-based method. It wasn't really a comparison it wasn't really a decision, should we do non-gradient-based or gradient-based? It was seeing how well can this algorithm, which has performed in classical settings very well, perform in a quantum setting.
I'm going to take one last question.
Yes.
Sorry if you mentioned this already, but are you trying to minimize the cost function here?
Yeah, we're trying to minimize our cost function.
Okay, in that case, there isn't really point, but would you not want to take the square root of that and possibly do it? Because if you're...
The square root of this?
Yeah.
So
it wouldn't be a difference, but like ideally, technically, you're taking the square root of that function?
No, so what really matters with these cost functions, we found out more heuristically, is this cost function itself differentiable and analytic in the complex plane. So if you take the square root of a function, you diminish that ability. Because unlike in traditional machine learning applications where we are only dealing with real value functions, in our case, our entries can be complex value. And so that is is a key part of this. But yeah.
You drew.
Cool. Yeah. If anyone wants to like read the paper by any chance, let me know. I'll send it.
We can send it by email to like all of us. Is that possible? Maybe.
Yeah,
like,
yeah.
Or Sarah can send it to the SPS.
Sure, yeah, I
Or you
can.
can send it to the SPS.
Sure, I'll send it over.
With the text that you created.
Yeah.